code that you may have already looked at last night. That's the example, the adv.mpi.tgz code, which is what we're going to be using for the exercises today. So I'm going to talk a little bit about it. Also talk a little bit about how we think about designing one of these codes. And we're going to use a very simple set of rules. So these rules are going to allow us to write code that looks very much like what you would write for a PDE solver, but it allows us to avoid saying PDE. Right. So there's this wonderful game called the Game of Life. It was popularized by Martin Gardner in a Scientific American article a long, long time ago, 1970 again, probably older than most of you. It has a lot of interesting behaviors. So you start with a certain pattern of cells, and there are rules for each generation in terms of what continues to live, what dies, what is born. And you can ask all sorts of interesting questions. So one question is, well, if I start with a finite number of cells, is there a bound on the number of cells? And surprisingly, the answer is no. That there's a thing called a glider gun, which creates a pattern that it fires off out into space. And it does that every, I don't know, it's like 54 generations or something. And so if you just let it run, the population just keeps growing. And I think somebody eventually found a glider gun that spits out glider guns. And so forth. The rules are also really simple. So each cell, we have a nice regular mesh. Each cell is either alive or dead. We give it the value of 1 if it's alive, 0 if it's dead. And at the end of a generation, a cell continues, or a cell is alive if it has exactly 3 neighbors, or it was already alive and it has either 2 or 3 neighbors. So if it's too lonely, it dies, and if it's too overcrowded, it dies. And if it has just the right number in an empty cell that has 3 neighbors, exactly 3 neighbors, gets filled in. And so here's an example. Each generation goes like this. And then in that case, and that's it, of course. Okay, so one of the ways to look at this is, well, how would I implement this in serial? So we create an array to hold the state. I'll actually do 2 so that we can easily swap between them. If I was really memory poor, of course, there were ways to avoid that, but this makes the code much simpler. We initialize it. In this case, we're going to have a fixed size world, and the edge is dead. And then at each step, we calculate the new states based on the previous states, and then swap. Okay. So pretty easy code. To do this in parallel, there are lots of ways to think about it. When you're building parallel codes, there's maybe 2 basic approaches. One approach is to start big and cut into pieces. And the other approach is to start with pieces and try to assemble them. Right? And again, depends on what you're doing, which one may be easiest. For these sorts of problems, I find starting big and cutting works best. So we start with what we would have with the sequential code, our global array as the main object. And we'll write the code in terms of that global array. And we'll define the decomposition in terms of that, define the communication of the data, and so forth. And then there will be the local arrays for each piece. Okay. So here's our global data structure. View each of these circles as a mesh point, not as a cell. or as a cell, this is the mesh points. If we were doing the differential equation, we would do, say, here's a 5-point stencil. For life, we have the 9-point stencil, so we also would have these 4 here. Okay. Now I'm going to decompose it, and I'm going to cut it this way. So one process will get this block, one process gets this, and so forth. Now when I'm doing my computation with life again, I'd have these 9. This one is easy because all that data is local. Oops. There should be, oh, there's the one, okay. So, but you, of course, for these ones on the boundaries, again, as I mentioned earlier, I need information from my neighbors, okay? So if I break this thing up like this, so here are each of these meshes. And if I've got, again, this sort of plus stencil like that, that one's easy. But for this one, then I'm reaching out over to this point there. So I have to deal with that. So what we typically do is add a halo or ghost cells. These are copies of the data for my neighbors. And for this simple example, it's just one set of cells. If I had a wider stencil, I might use a wider set of ghost points. Or if I took multiple steps per communication time, there's a way to trade communication for computation. Again, I think this is something similar to this approach was mentioned yesterday. Again, that might be wider. Okay. So in this case, we'll just have a set of size 1. And so for this execution, I need to fill in this data here, which I do by sending the data to my neighbors. So that's a 5-point stencil. Right, so just up, down, left, and right. Life involves the corners as well. So how do we do that? Well, one thing I could do is I could send this guy here straight up there and do the same for the other 3 corners. Right? And that might be the right thing to do. But in fact, as answer to your question, that's one, it's one word of data, it's actually one bit of data that I'm sending for life, right? So there is, in fact, another way to do this, which is fairly easy to describe in this case. Pretty much can always be done, but gets complicated with unstructured meshes. And with that, what I do is I do my communication in 2 steps. So here first I'm going to send my left and right edges to my neighbors. Okay. Now notice what that does. That means it's filled in, it's taken this point here. Remember now this piece here, this point there, needs to go into this halo cell. Right? I need to take the corner of my mesh and send it to my diagonally across neighbor. Okay, so I've taken that data and I've sent it over here. Okay, and the same thing's happened. So this guy has sent this piece of data over to here. Right. Sent this one into that edge. So now I move that entire edge up here. And so what's happened is that this piece of data went from here to that corner. So in 2 steps, only moving large data, or largish data, I moved that diagonal. So I didn't have to do the separate communication move. Okay. So it's good and bad. So you've seen the good. What's the bad part here?
The communication is synchronized.
Yeah. So there is an order here, or a partial order, right? So I can send to my left and right neighbors, and I don't care the order in which that happens. But I can't start sending up and down until both of my left and right edges have arrived. So instead of having, say, this is essentially the same as having one weight all, I have two. So whether this is good or bad then depends on sort of relative performance and the benefits that you get from that. But it does mean that you avoid quite as many sends. And remember, I mentioned that the latency, the cost of doing anything, any communication at all, hasn't really gone down very much over the last 10 years. It's still, for the very high performance systems, it's still on the order of a microsecond or so. And that's what it was 10 years ago, whereas the bandwidths have continued to go up. Right? So this approach trades a few more synchronizations for fewer communication steps. Okay. So in terms of the local data structures, the way the code is arranged, each process has its own patch. There are various indices in the code, and they were picked to reflect back on the original global code. So it very much wants to think about the problem as that original sequential code. And so things with a G in the beginning are global. They refer to the global data structure. So this is this GJ gives you the J index of the first column of the local patch in the global array. So it tells you where to put it that way. And GI does the same thing for the I index. Right. Ls are local. So LNJ gives you the local number of values in your part of the mesh. Okay. Your part doesn't include the halos. The halos are a communication optimization. They're essentially your cache of the data that you need to perform the life evaluation or to perform the stencil. And the same thing for LNI. Okay, so the program has these pieces. There is MLife2D.c. This is the main program. These are all C codes. I almost have a Fortran version ready, almost. So if you absolutely cannot read the C code, come and talk to me. I hope most of you can read the C code, though. It's fairly straightforward, and we'll talk about the few places where it may be a little obscure to Fortran programmers. This main program runs life with 5 different choices of this halo exchange. So the code is structured to make it very easy to do different sorts of exchanges. It runs each of these twice. Why twice? Well, timing codes is much trickier than you think. We still get bug reports when people have run benchmarks that are not sophisticated enough. And they say, oh, why does it take so long to do a send? Well, it was because they did MPI init time, MPI send time. Well, what happened on the first MPI send was it built the entire connection structure out to wherever it was sending it to, and you timed all of that. The second send took 1/10 as much time. Right? On some systems, for example, the first time you execute the code, where is the code? It's not in your processor. It's on the disk. So the first time you execute the code, you may have to wait for it the code itself to arrive. Right? And the same thing for the data. Where is the data? Well, the data may not even exist yet. Right? The memory location may only be virtual, not in the virtual memory sense, but really virtual until it's actually instantiated. So for example, when I ran some of these on a Cray, I got very different times the first time and the second time because of these sorts of effects. Running just twice is really not enough, but it's maybe the absolute minimum to do. And then it prints the time taken for each of the for each of the iterations and for each of the exchanges. So you can see how much time is taken for the whole generation step, including the computation, how much time is taken for the communication. Okay. There is a file in options.c, which has a routine that parses the command line options. So that's where you can look to see what the options are. And if you want to change the code to do something else, like, for example, just run one of those exchanges at a time, that's where you would modify the code. Patch.c is the one that computes that local patch. And there's a couple of things that have to be done with that local patch. So first is, how big is it? The next is, where is it? And then the third is, how is that patch or that decomposition of the global array mapped onto the physical hardware? And so you'll find routines in there, one that does a decomposition onto COM world, and one that uses the MPI topology routines. It uses cart create. How many people know about cart create? Okay, just a couple of you. So we'll be talking a little more about that later. And then it returns the information in a struct. mtiming.c contains a routine that actually does the execution and returns the timing. Let me say right away that this loop, which includes a function call, is absolutely guaranteed to give you terrible performance. So in part, it's sort of a stand-in for, let me do enough computation work to make it interesting. But it's not meant as a model of how to write the code. This is exactly the wrong thing to be doing with this kind of code in principle. For Fortran users, you'll see icky code like this. This is just a way to call a function that's been passed into a routine. In Fortran, you would have just declared it as external and been done with it. It swaps the arrays. So you could do this in modern Fortran with pointers and target qualifiers, or you could just do 2 steps switching between them, which is a common way to implement the code. Okay. Then there are files, one for each of the possible exchanges. So this gives you a hint to the exercises, which is to try something different. You write a new routine. So for example, this point-to-point, it uses this, what's called the diagonal trick, the thing that moves the data to the diagonals by moving it first to the side neighbor and then to the up or down neighbor. You can contrast that with this one here, which does not use the diagonal trick. So this one has twice as many communication steps because you've got 4 side neighbors and 4 diagonal neighbors. And see how that looks and see how that performs. There's one that uses send and I receive instead of I send and I receive. There's one that uses user packing and unpacking instead of vector data types. Rajiv will be talking about data types, but in that, if I go back to this, right? So this nice local mesh, these cells in, depending on how I write it in C, either the row or the column are going to be contiguous, and then the other ones are going to be strided. They're going to be, this cell is going to be LNJ plus 2 from this cell and so forth. And so to send those, what do I do? Well, one thing I can do is I can read those out and put them into a contiguous buffer and send them. But MPI provides a way to simply say, the data that you want to send is not contiguous. It's described as, for example, every 27th word. And that's with MPI data types. And that can be better. Again, depends on the implementation. Okay, and so that's, there's an example here that does not use the data types. So user vector here. So you can see which one's better. And this may be important as you're looking at optimizing real codes, because done well, using the MPI data types can give you a significant performance advantage. And there's a paper that, in fact, that Torsten did a couple of years ago that showed an example in a couple of cases. But it depends on the MPI implementation being really good for that. And that's rare. So sometimes you want to do it, sometimes not. Again, it's good to design your codes so that you can easily take advantage of this when it makes sense and do something else when not. And then the last one, which is another thing that we'll be talking about this afternoon, is using one-sided communication instead of two-sided communication to do this. So we'll use this one example to illustrate essentially everything. Each of those files implements three functions. There's an init, an end, and the exchange itself. So the init creates any persistent data that's needed for the communication. So in some cases, there is no persistent data, but in some cases there is. In particular for the RMA, there is. Then the end frees any such data, and then the exchange, in fact, does the halo exchange. So that's all you have to implement to add a new example. And then there's a simple I/O version. We've got, it's not included here, but there is more code that, for example, shows how to use MPIO to output this data, and also shows how to use an I/O library like PNetCDF to output this data. This one just uses I/O to standard output, so it does something which works and is okay for some codes, but again, is often to be avoided, even though you'll see it in many cases. It sends all of the data to one process with rank 0, who then writes the data out. When you are writing to standard out, that's the only safe way to do it, because again, when you do a print or a printf from your program and it returns, that doesn't tell you anything about what has appeared on your screen. When the data appears at your screen is up to all sorts of intervening layers of software. So if you absolutely have to have a specific order to standard out, you absolutely have to go through one process. If you don't care, then you can be a little more flexible. But if you're really, really depending on an exact behavior, the only way to get it is to go through a single process. So that's what this does. And it has some limitations. It can only handle a mesh of width 256, and it has to fit on your display. So, because it uses Xterm and ASCII terminal command sequences to draw. So, essentially needs a sort of standard terminal window. It also has an init and a finalize, and there's a routine called checkpoint. The checkpoint is the thing that does the output. So we wrote this as an example. If I'm doing a mesh code and I want to write out my solution, and maybe I want to be able to read it in, then I've got a checkpoint and I've got a restart. Now in this case, if you wrote it out the standard output, it's gone, effectively. So there's a query for can you restart? The answer for this is false. But if I wrote to a file, the answer would be true. And so again, like I said, even though we don't have time to talk about it here, because you've got so much more to learn, there are examples that use I/O, and if you if you want an extra challenge, I'd be happy to show you those codes. Okay. So again, it gives you a nice general interface, gives you a lot of flexibility. It doesn't tie the code down to a particular choice, allows you to swap things in and out very easily. And building it's pretty simple. There's a configure. In fact, you just give it configure on Vesta, and you've loaded in one of the compiler wrappers. Just raw configure should be fine. If you want to force it to use a particular compiler, you do it this way. You say MPICC all in uppercase equals the name of the compiler you want to use. Once configure is done, you should be able to do make. If you're running it on your laptop or you're using MPI-CH or OpenMPI, then MPI exec will work. And so this is an example of running it with a 1,000 by 1,000 mesh for 100 iterations. If you add this -C, it will do the visual display. Okay. And so with that, are there any questions? It's sort of a view of the code. So I've talked long enough. So what we'd like you to do now is, if you haven't already, go ahead and build and run it. Try it with large enough meshes. The default size is meant to allow you to run it on your laptop and see the output. But you can run it with large enough meshes to get some interesting times. And then you can try making a change. And whatever you want to do, and you can try this on your laptop first to make sure it works. If you know about persistent communication, you could try that. Rusty mentioned the ready sends yesterday, so that's another thing that you could try. You could also use the MPI send receive call, or you could try anything else in terms of, you could try switching the orders of the iSends and iReceives to see if it matters. It's like we talked about. And then you have to modify MLife to DC to call your new routine included in the timing output. So give that a try, see what you come up with, and we'll be circulating around to answer questions.